This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you enjoy the Future of Everything podcast, please subscribe or follow it on whatever app you listen to your podcasts on. Today, Jonathan Osborne will tell us that we need to train our students to detect misinformation starting at a very young age, especially with science education. There's a lot of fake science out on the internet, and we need to teach young people how to tell the difference between what's true and what's false. It's the future of science education. Before we jump into this episode, a reminder to please rate and review it on your favorite podcast app. It'll help us grow, and it'll help other listeners figure out what this is all about. Science education is absolutely critical, and these days the internet is filled with bad science. And yet science is wonderful. It's like a miracle. It gives us insight into how life evolved, how the planet started, how the world works. So even in grammar school and in middle school, we need to give students tools to be suspicious about things that they hear and to figure out if what they're listening to is from a reliable source, an expert, and something that they can take to the bank. Jonathan Osborne is a professor of education at Stanford University, and he studies science education. He's worried about misinformation, and he'll tell us that the situation is pretty dire, and we need to act soon to make sure that we outfit the future generations with the tools they need to navigate truth and falsehoods in science. So, what is the state of our educational practices for young people in preparing them for this world?
The short answer to that, which I will elaborate on, is not good.
Okay, and please go on.
And it's not good, really, I think, for two fundamental reasons, really. One is there's a kind of delusion out there by people involved in educating people about science that by the time they get to the end of high school, they'll have enough knowledge to evaluate the evidence for themselves. And this means that they don't need to rely on experts, and the internet reinforces that in that kind of way because you've got access to this unlimited information. You think, well, why do I need to go to an expert? I can look it up for myself. And the answer is you don't understand what they're talking about is one of the reasons. So that you need to generate what I would call more epistemic humility in people, which is to recognize that our knowledge is bounded. And there are times when we have to call on experts. But what you notice with a lot of the misinformation sites is they understand this and they appeal to your ego in the sense of evaluate the evidence for yourself. You know, you go on 9111truth.org, for instance, and you'll see up in the top left, okay, evaluate the facts for yourself. Well, the facts have actually been cherry-picked and you don't actually have the ability to evaluate the facts for yourself. So that's one of the reasons, I think, really, and we've got it the wrong way around. We actually have to start by saying we have to prepare students to interact with scientific expertise. The question that invites is...
Yes. Okay. So we're going to get to how to do that in a moment. I was hoping in preparing for our interview that you were going to tell me that because these young people are growing up in the era of the internet, they have received a special pre-inoculation to misinformation, and that therefore they're in much better shape, and that actually it's our generation who grew up way more trustworthy who is having trouble with the internet, but they are having less trouble. It sounds like that's not your message today.
That's certainly not my message, okay? It's not the message, it's not particularly my research, but it's the research of all my graduate students, it's the research of my colleague Sam Weinberg, which shows that actually they are really poor. Because they are deluded into thinking that they can work out the evidence for themselves. And time again, when you show them a dodgy website from the Hartland Institute about climate change or something else, they will stay on the page and try and evaluate the arguments on the page, which they don't have the expertise to do. What they should be doing is not saying, is this correct, which they can't work out the answer to. They should be saying, is this credible? And they are not good at doing that. In fact, they're probably worse than our generation because we've been around long enough to think, this looks a bit dodgy.
Yes. Okay. So what do we do about this? I mean, this is your area of expertise, science education, especially in grammar and middle school when, the minds are being formed and the intellectual habits, so to speak, will be created. What do we need to do?
Well, you really need to do three things, I would say, but one of them is pretty immediate from that point of view, which is that if you're confronted by any scientific claim, there are really three things that you need to do. One is you need to ask, is the person or the institution putting this forward, do they have a conflict of interest? So if it's an institute, who funds it, for instance, in that sense? And if you open another tab and you put in the name of the institute, you can pretty rapidly find out who's funding it, for instance, say by the Heartland Institute or co2science.org. From that point of view, you can do that. And so if there's a conflict of interest, that raises a red flag.
Right.
Okay. If there isn't a conflict of interest, then you've got to say, well, okay, is the person making this claim a credible card-carrying scientist in that discipline? It's no good having an evolutionary biologist making claims about cosmology or vice versa. They don't do that in that kind of way. And this is the kind of stuff that's not taught to students. What makes somebody, being a scientist doesn't mean very much. It's a scientist in the discipline. Is it a credible institution? What are the credible institutions in that way? And then the third question you've got to ask is the goal of science is the achievement of consensus. Right. And so if there is a consensus and somebody is going against that consensus, for instance, like Robert Kennedy Jr. on vaccines, they better be an expert and they better have pretty good evidence for they're questioning the consensus. I mean, again, these kind of purveyors of misinformation know this. On climate change, you've got these fake consensuses, the Leipzig Declaration of non-experts. None of them are experts in climate change. Now, somebody might say, oh, that's all a bit dull. How are you going to teach all that?
That's exactly what I was going to ask. I was going to say, it's so fun to read the conspiracy theories about science, and what you've just outlined sounds so reasonable, and I can't imagine getting a 12-year-old to take the time to do that.
No, okay. You get them to do it by giving them a challenge or a problem, okay? You're saying, okay, should we believe this website? Okay. You group of three can look at it and see if you can think of arguments for believing it. You group of three can look at it and see if you can find out arguments for not believing it. So you learn this by doing it in that kind of way. And then, once you've engaged in it, I think the messages can be built on to say, well, why didn't we believe in this? This person, he had a PhD, but what was the PhD in this way? It's kind of detective story for them in that way. So it all has to be learned by doing it.
When are young people cognitively able to kind of understand the challenge that you just outlined and start implementing it? Like, I can imagine, you talked about credentials. I'm thinking about my 5-year-old grandson. Credentials are not a thing in his life yet, but they will become a thing, at some point. So how do we developmentally do appropriate things at the various stages of schooling?
Yeah, that's a good question. And I'm going to have to be honest and say, at the moment, it's all kind of based on a hunch of what we can do. All I know is that we produced this report last year about science education misinformation, and one of the significant contributors to it was a guy from Finland who's been working on developing a Finnish curriculum in media literacy. And they start in elementary school, obviously about grade 3 and 4. Right. They give them simple kind of exercises, trying to check whether this is factually correct. And then they keep building on this and building in more complex issues as they go up. So, I think, to be quite honest, the answer is, well, what you're really asking for is a kind of developmental learning progression. What are the basic competencies? What are the higher order competencies? And I don't think we've really mapped that out yet from that point of view. But I think the kinds of things you're asking about, we're asking about are a conflict of interest. I would have thought you can easily do that in middle school in that way, because they're starting to get a sense of, well, is this funded by the tobacco industry? Is this funded by the oil industry? Who's paying for this?
Yes. So this is very good, and I know that this touches many of the other things that you've looked at. One of the things you've published a lot about is student attitudes towards science and towards learning science. That has to be intimately involved with this because they have to care and they have to have some sort of model of science. So, separate from the issue of misinformation, how are we doing at giving, especially students who are not going to be scientists, the fundamentals to be a citizen in 2023. And by the way, I should say, let's take a moment to say the reason this podcast exists is because I perceived in 2016 that maybe I could make a small contribution in increasing the understanding of science and technology and engineering by bringing it letting people tell their stories so that people could see that these scientists are people motivated by passion and also motivated by the search for truth. So I'm very interested in your thoughts about where we are and how well we've prepared people to even engage with these issues.
I think the history of science education, really ever since its sort of formal inception, is not very good. The simple reason for that is if you look at the rationales people give for science education in the past, ever since they insisted that everybody must learn science, is they say, oh, well, it'll enable you to be a critical consumer of science, of scientific information. It'll introduce you to the beauty and awe and wonder of science and the intellectual and creative achievement that it is. The answer is it doesn't. And why doesn't it do that? Because it's the final goal, which they sort of add on at the end, which is the preparation of the next generation of scientists, which predominates. And the form of education you've got for that, as you yourself probably know, and I've been through it, is you have to go take the long slog through the dark kitchen before you get to the hall of awe and wonder. Yes. And most people lose interest long before then. And another way, I think, of testing this is you say to any of your non-scientific friends, what do you remember of value from your school science education? Now, I'd guarantee that most of them will mention some sort of funny flash bang bang experiment or whatever it is. But then you say to them, yeah, okay, I understand that. Yeah, that was exciting. But what idea do you remember that really changed how you think about the world? And I think you're going to get a lot of them hesitate. In that sense. Now that to me is a tragedy. And it's a tragedy because science is one of the great intellectual achievements of our contemporary societies. And that has not been explained to them in that kind of way. And it's not explained to them because it starts with doing all this kind of detailed stuff about forces, interactions, cells and their function. Now, I'm not going to say you don't need to know some of that. I'm going to say that we're doing it from the wrong end of the telescope. What I want is the big idea, first of all. Look, you live on you're one of, I don't know, I think it's 8 billion people, one of 8 billion people living on a tiny planet circulating a sun, which is actually a star, which is part of millions and billions of stars, which is part of millions and billions of galaxies. How do you think we know that? That's crazy from that point of view. Yes. Or the obvious explanation for day and night is that the sun moves. I mean, after all, you get up in the morning, okay, and it's in the east and it goes to the west. I've got a crazy idea to tell you. No, I'm sorry, okay, we're on a spinning earth. How do I know that? Or even, what about all these people who think the earth is flat? Okay, why should we believe that the earth... Now, then I think you sort of start to engage people. Now, I'm not saying everybody from that point of view. A lot of it's about applications. Some people really want to know about the applications of science. How does your TV work? How does your computer work? And there's that kind of story to be explained as well, and that's fine. But if you, as I say, if you concentrate on the bricks of the edifice and you never show what the edifice is about, then not surprisingly, a lot of people think, well, what's this? There was a science educator in the 1952 wrote a paper about this, and he said, well, most people end up with a miscellany of facts. I mean, some of those facts are useful, undoubtedly. If you go to the doctor, it does help to know some facts about the structure and function of the human body. But I do think we really ought to say, what are the big ideas that people should carry away from their science education, so that when you ask my question, what do you remember that changed your thinking about the material world, people, and how do we know that's true to people? You put that question to people, they would give you some decent answer, and they don't.
So that is you've made a compelling case for that. And let's just go down to the nuts and bolts, because as a professor of education, I think you'll know this. Who do we have to convince to change things? Because I don't think many of us know who holds the keys to the curricular practices at all different stages. I know as a faculty member, I have some say in how my discipline is taught at Stanford University, but really before that at the grammar school, is this boards of education? Is this textbook writers? Who do we have to appeal to make these changes?
Yeah, you're asking the really important question, I think, and I'm reflecting on a career of trying to make these kinds of changes for the past 25 years, and what I've seen time and time again is when you make the convincing argument. We had a report in 1998 called Beyond 2000 Science Education for the Future. We needed a different form of science education in the UK. We managed to convince a lot of people. We managed to convince the people, the equivalent of the Board of Education, who set the curriculum. There was a curriculum written and it was all put into place. But there's resistance, okay? There's resistance from what I might call institutional conservatism. And then there was a change of government with an emphasis simply on knowledge and not knowing any of the other features of how science works in that sense, or ideas about science. And so it got killed. And actually there's a similar thing going on at the moment in California with Algebra 2, which is in 2019, I don't know if you read about this, but in 2019, it was agreed that this course on data science done by my colleague Joe Bowler would be an alternative to Algebra 2, but it's currently being killed by the complaints from various people, and the California Board of Education is about to say, well, it's not rigorous enough, so that's going to get killed. Right. So I've kind of reluctantly come to the conclusion that people like me or people like you or trying to write curriculum and change it is unlikely to happen. The problem we've got at the moment is a system where there are not enough gaps or opportunities for teachers to pursue their interests and their student interests. So I think actually the best thing that we can do at the moment is to say that if you impose this curriculum, which is supposed to be for science for all, and then you insist that 99% of the time is devoted to that minority, this is wrong. You have to cut that back significantly. So the current standards, for instance, there's 200 performance expectations. They're not all the same level. Cut it to 100. Give that teacher freedom, respect their autonomy, respect them as a professional, give them agency to do some of the things which they think matter to their kids here and now. And into that space, obviously, people like me, people like you can say, have you thought about doing this? Have you thought about doing this? Have you thought about doing this? And I just think it's got more chance of changing the education, because after all, and you probably know this as well, my motivation for science, I think, came from an early age. I was just fascinated by things, and I kept going through the long, dark classical electrodynamics being the one that really nearly kills it all. But interest is what carries you a long way, and interest is generated by the teacher. And the teacher has to have enthusiasm, and they have enthusiasm if they've got agency in that sense. So that's my current take on it, but I haven't got any proof of that, but that's just my reflections of now.
This is The Future of Everything with Russ Altman. More with Jonathan Osborne next. Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Professor Jonathan Osborne from Stanford University. In the last segment, Jonathan told us some of the concerns he has about misinformation about science and some of the tools that he believes we need to give young people, even grammar school and middle school students, to make sure that they can learn to vet the information they're presented with. In this segment, he'll tell us that there are different forms of scientific argumentation, and they don't all get the same attention from the press and from teachers. He's going to argue that we need to give teachers more freedom to introduce scientific arguments of a wide variety and ways to check that they're all sound. So, Jonathan, in your work, you discuss argumentation and teaching scientific argumentation. You made a little bit of a reference to maybe we should set up teams of middle schoolers who figure out if a website is good or bad or reliable or not reliable. But more generally, tell me, what is this idea of scientific argumentation, and where do we want to get students in terms of their ability to understand or even implement argumentation?
Yeah, I think basically, argument is core to science. That's what you and I are doing. If we write any kind of paper, we're mounting an evidence-based argument on the whole, or it's a theoretically based argument based on scholarship to convince people that some of the claims we're making are true. And the trouble with a lot of the teaching of science is that students are introduced to a lot of entities of what you might call an ontological zoo of rather strange entities, ions, atoms, molecules, and stuff they can't see. And they have to really accept it on faith because they're taught it by their teacher. So in some senses, it often almost, from a lot of students, acquires the aura of a religion in that sense. Now, it's not a religion, it's an evidence-based argument. And you can illustrate that with all kinds of arguments at any kind of age from that point of view. So, for instance, one of the ones we were talking about is, how do we know that the Earth is a sphere rather than flat? After all, it looks flat. Why should we believe that it's a sphere? What's the evidence that convinces us of that? I had a wonderful one in my own education, for instance, which is that we spent, I think this was again in middle school, we spent about 3 weeks growing copper sulfate crystals. That was great fun. We had a big competition. Who's got the biggest one? Okay. And then the teacher said to us at the end, he said, "Oh, what do you know about these copper sulfate crystals?" And we looked at them and said, "Well, they're all blue." Okay. I said, "No, haven't you noticed something else?" "What was that?" He said, "Oh, well, yeah, they're all the same shape." "Oh, yeah, they're all the same shape. Yeah, but they're different sizes. How could that be?" He said. Okay. And we said, don't know, scratching our head. And he said, "Have you ever been to the greengrocers?" And we thought, "Yeah, what's this got to do with that?" Okay. "You notice the stacks of oranges?" "Yes." Okay, you said. "Okay. Have you noticed it doesn't matter if it's a big stack or a small stack?" Okay. "They've all got the same lines and shapes, okay, but they're made out of particles which we call oranges. It's just like that with your copper sulfate. It's made out of particles in the same kind of way." And it was a wonderful, elegant argument for particle theory of matter in that sense, which has stuck in my brain ever since, because I tend to react to good arguments and think that's good. And that kind. Now, I'm just asking for more examples of that. I mean, for instance, what's the evidence that we believe in the theory of evolution? What led? And there are stories to be told about that. And kids like stories, because stories are the things that you and I use to communicate all the time. We use them as evidence in that way. And we don't tell enough stories about science. Now, part of that actually is the problem that actually a lot of us don't know the stories about science, because we were never told the stories about science. So how do we get out of that kind of cycle? But
it's funny that you say that about people, because I'm very aware. One of the early scientific mentors I had said, science is a great career, but one of the things you have to become comfortable with is that your discoveries may be remembered long after you are forgotten. And so, and there is truth to that, because the discoveries are kind of the goal. On the other hand, as you just pointed out, the stories are very important in order to keep people engaged and thinking about that this is a human endeavor. We're not robots, we're not ChatGPT, and that we're deciding what questions to ask, and then we're trying to answer them, and we're doing the best that we can, and it's an imperfect, approximation. But so I'm really struck by your statement about stories, because I agree with you, and yet we were told as young scientists that it's not about your story, it's about the knowledge that you create, and that might have been wrong.
Yeah, that might be wrong, but also there's a story about how that knowledge was created in the first place, and that kind of. And it's often quite a complicated story in that way. I mean, just take something simple. Okay. Well, maybe not so simple, but vaccines. What's the story behind vaccine? Okay, how did people first have this crazy idea of putting a disease into somebody in order to prevent them being infected? It just sounds wrong in that kind of way. So where did they get that idea from? And what was the path that led them to it? It wasn't something that was instantaneous. It wasn't one lone genius working on their own. It was a succession of work done by different people. Certain names stand out in that process. Obviously, Jenner and Pasteur. But
as you look at scientific argumentation, is it different across fields? Do physicists and biologists make similar arguments, or have you seen differences? Are those differences important?
There are basically three forms of argument that are made in science. Okay, one is the hypothetical deductive argument, which predominates a lot in physics, particularly when mathematics is involved. Or increasingly, there's quite a lot of that in biology as well, with some of the models that people are developing and making predictions on the back of models. But the second form of argument, which we often forget about, is the abductive argument, which is the inference to best possible explanation. That's the form of argument that I just illustrated for you with the story about argument for atoms. This is an inference to the best possible form of explanation. It's the form of argument that Darwin used with the finches. It's the form of argument that Wegener used for continental drift in that kind of way. It's quite common. We're confronted with complexity, and we have to look at it and think, well, possibly this is happening. This is the best fit with the evidence. And then there's obviously the inductive argument that you make, for instance, that all metal oxides are bases is the obvious kind of one. All mammals are warm-blooded. Those are inductive generalizations which we have to make because we've got to make the world simpler than it appears in that way. So they do vary across the I couldn't go through all the arguments used in all the sciences, but I would say I think that there is more use of inference in biology than there is in physics or the physical sciences, I think. Yeah.
Yes, and that makes sense, and I like that because as you were describing these three different modes of reasoning, they're all present in all fields, but I think some of them are used more in one field than the other. The physicists have their mathematics and they like the deductive mathematical approaches. The biologists are overwhelmed with observations, don't have much theory, and so they wind up doing inference from observations without too much of a deductive theory. So yeah, this actually makes sense. So do you think that this needs to be made explicit, or is it best for students to learn this a little bit more in a subtle way by example? I'm not sure you would want to give those three. You would maybe in high school or college, but for the middle schoolers and the grammar schoolers, you probably want them to experience those logics before you name them. But I'm asking.
Oh no! I think you definitely want to experience them before they name them. But I just think, the problem with the description of science, the standard introduction to the scientific methods, it just tells you about the hypothetical deductive method, and so it makes to me it really is an insult to science because it makes it seem like it's some kind of algorithm. You just turn the wheels and you get this. Yes. Okay, there's no creativity or intelligence that goes into it, or imagination that goes into it. But actually, it's. If you look at I have this thesis that basically most of what you're teaching as science is a set of crazy ideas from that point of view. The idea that the air has mass, the idea that you look like your parents because every cell in your body carries a chemically coded blueprint about how to reproduce you. Who would ever have conceived of these ideas? Okay. And so you have to once you see yourself as a teacher of crazy ideas, you start to realize, hey, I've got to convince people to believe in basically what they're all going to say. Why would I believe that? And then you've got to make use of evidence to convince them of that. And then you start to see the richness of the story.
So that's very good. And in our last minute, I just wanted to get to this issue of timing. In your comments and in your writings, you've talked about we should have a sense of urgency. The rate at which teaching standards are updated may not be ideal at a time when the world is moving very quickly. So talk to me about this sense of the time scale at which science education should evolve.
Well, basically, the problem with the most current set of standards, I would say, internationally at the moment, are the US ones, which are the framework for K-12 science education. I was on that group. We wrote that in 2011. Looking back now, I think we made all kinds of mistakes. This is inevitable. What's really happened is the context has changed enormously because all of a sudden you have the rise of Web 2.0, the rise of misinformation, and we have no capacity to adjust for that because the next set of standards will not be written for 10 years. This, I think, is why I'm going to argue that actually you have to create any set of standards you have to create with space for people to add, adapt them, and make them. And that's terribly important for the teachers because they're only going to really teach it with passion if there's a sense of ownership. And they only have a sense of ownership if they have a sense of agency. So you have to leave space in standards for that because you cannot predict what's going to happen in the next 10, 20 years that might need addressing. And that's the problem we've got at the moment.
Are there bright ideas about how to give the teachers that freedom? I'm sure the teachers are in favor of it.
Oh, yeah,
a subset of the parents may be in favor of it. I don't know about the politicians.
Well, I think it's the bright idea is less is more. Okay, you look internationally. Okay, and there's clear evidence that some of the countries that have less time do a better job in that sense. because they have a clearer sense of which goals they want to achieve, rather than sort of like spreading it across, well, we've got to do all of these. Okay, these are the ones that really matter. And so it's our responsibility as science educators, as scientists, to say, this is what really matters. The rest of it's up to you if you're particularly interested in it.
Very good. Thanks to Jonathan Osborne. That was the future of science education. You've been listening to the Future of Everything podcast with Russ Altman. If you enjoy the podcast, please follow or subscribe. If you like it, or even if you don't, please rate and review it so that others can learn about the podcast. We have a back catalog of more than 200, now pushing 250 episodes. Check those out. There's some good stuff there, and it's still the future of most things. You can connect with me at Twitter, at @RBAltman, Threads, at Russ B. Altman, and you can follow Stanford Engineering at Stanford ENG.